Hey everybody, welcome back to Organic Chemistry. My name is Todd Rothman, and we're now on section 8. And this is the second to last section for the chapter. So what we're going to do at this point is we're going to focus on the preparation of aldehydes and ketones, and then we're going to talk about oxidation and reduction. They're not the same topic, but they're small enough that I could put them into one video. Okay? After we finish these two topics, we're going to wrap this video up, and then we're going to finalize with a bunch of problems for section 9. Okay? And that's just going to wrap up the whole chapter. All right, let's get started. So the first thing we'll do is talk about, number one, we'll talk about the preparation. Okay, so preparation and A of aldehydes, or I guess I'll just write aldehydes, because we're going to have a few ways to do it. So aldehydes. Now, A, the first one is dealing with alcohols, in particular primary alcohols. So if I have, let's say, a primary alcohol, and I was to write PCC, remember how this is last semester, nothing really new that we're going to learn about right now. This is all review from last semester. Well, PCC was a way that we can partially oxidize. And so what that did is it allowed us to make a double bond O, but that's it. It didn't go any further. So remember how like KMNO4, CrO3, they oxidize completely. But PCC would take a primary alcohol, any type, and just make it into an aldehyde. Okay? So that's the first way to make an aldehyde. Now, and this is really the only one for oxidation. By the way, this is in CH2Cl2. It's just a reagent. If you write PCC, you're fine. You don't really need to write that, but that's really what it would be in. So that's one way. Another way to make an aldehyde is to reduction of class 2. Now, we didn't talk about class 2 yet, right? Carbonyls. But we should know at least how to make aldehydes from it. So, for example, an acyl chloride is one reagent. Now, I want to say that what I'm going to show you, I'm not going to go into the mechanism. At this point, I'm just going to show you the answer, but we'll learn the general mechanism in the next chapter, okay? So really, this is just for organization purposes, and we just want to, kind of figure out how can we make an aldehyde. So the goal here is to take the Cl out and to put an H in its place, right? So we want to replace the Cl with an H. And the way that we do that is by using this partial reducer. It's LiAlH, and then it's tert-butoxy group. So OTBU 3 times. So we call this tritert-butoxy lithium aluminum hydride. That's the name of this. Okay? And then step 2 is water. Now, what this does, without going into all the details, is that this one hydride right here, this H, is going to wind up coming in. It goes in as a hydride. This is going to open up, but double bond O, and then it's going to close back down, and this is going to get thrown out. Okay, we're not going to go into the mechanism until the next chapter. So for now, that's all I want to say, is that acyl halide can become an aldehyde by simply using lithium tritert-butoxy aluminum hydride. Okay? All right. Now, another possible scenario is an ester. An ester can do this, but instead of lithium aluminum tritert-butoxy hydride, what we use is DIBA, diisobutyl aluminum hydride. So it's DIBA, or sometimes you'll see this DBAL-H, same thing. It's the same thing, DBAL with an H, because it's diisobutyl aluminum hydride. So it's either DIBA or DIBAL-H, same thing, okay? And all that is a partial reducer, and it does the same thing as with the acyl halide. This H is going to come in, this is going to open and close, and this is going to leave. But it happens one time, so you wind up getting an aldehyde. Okay? So it's the same logic, just a different reagent. Okay, and they're called partial reducers. They don't go all the way down to the alcohol, which is normally what they should do if you have LiAlH4, for example. Okay, and then the last one that I showed you guys this actually is review, is a nitrile. So with diisobutyl aluminum hydride, DIBA, this hydride is going to go into the carbon that's triple bond, while this becomes a double bond N. So you get R, C with an H, double bond to an N. Okay? And by the way, step 2 is H2O. Now, from here, if that's all I did, we would call this what's known as an imine. Step 2 is H2O. And that protonates the the N on top. So this would, the hydrogen would come in, right? Hydrogen comes in, and then the nitrogen becomes negative, but then water protonates it. So you make what's called an imine, which you don't need to know about this right now, the ideas about imines, but what you do need to know is that if this right here is in water, it goes further to become a carbonyl. So the N is replaced, the double bond N is replaced with a double bond O. You don't have to worry about how, because you didn't learn this mechanism yet. Okay, you won't learn about this until later on after this exam. So don't worry about how this happened. So these are the 3 ways that you need to know how to make an aldehyde from a class 2. Notice carboxylic acid is not in here. So for carboxylic acid, if you want to do a carboxylic acid, there is no trick. There's no trick like above. Instead, what you would have to do is LiAlH4, right? That would bring it down to an alcohol. Remember, this is last semester that we talked about LiAlH4 with any of these, the acyl halide, the ester. With this, it becomes an amine, but the other two become alcohol. So you'd have to go all the way down to an alcohol and then PCC it back up to an aldehyde. See, there's no one trick like DIBA or LiLH, OTBU3. There's nothing like that for carboxylic acid. Okay? So that's my point here. All right. So that covers the ways that you could make aldehydes. There's one more actually that you can make an aldehyde, but it actually covers both aldehyde and ketone. But I'll show you now. The last way, I guess this is C, is ozonolysis. So if you have an alkene, and the alkene is either going to have a primary side or, a secondary side or a primary side, right? Meaning there's only one carbon touching either one of them, right? So one or less. Then what's going to happen here, actually one or two I should say. So this carbon on the left has 2 carbons touching it. This carbon on the right has 1 carbon touching it. Well, when you do ozonolysis, O3 and zinc, then you break the double bond O and they become break the double bond and they become double bond O, right? So here's the yellow carbon right here, and if it has H's on both sides, it's formaldehyde. Here's the red carbon, and if it has 1 carbon touching it, that means it has an H, and that makes it an aldehyde. So ozonolysis is also a way to make aldehydes. See that? By just simply breaking the alkene. It's always going after alkenes. And as long as the alkene carbons have H's on them, then they're going to become aldehydes. Okay? So alkene carbons have to have H's on them. All right, so that's another method. So this is different ways that we could make aldehydes. And now let's talk about making the synthesis of ketones. So for ketones, there's similar ideas, right? So for A, we could do, instead of a primary alcohol, we could have secondary alcohols oxidized. Okay, so notice how for primary alcohol, we make an aldehyde. But if this was a secondary alcohol, like that, then if I use PCC or KMNO4 or CrO3, it doesn't matter, because in all cases, the carbon secondary with an OH becomes just double bond O, ketone. Okay, so in this case, it doesn't have to be PCC. It can be PCC, KMNO4, CrO3, and they all do the same thing. And by the way, any Cr group, not just CrO3, any Cr. So if you see a chromium, then you know it's oxidation, right, from last semester. This is all review from last semester. Okay, B is ozonolysis. So if you have an alkene that has no H's on it, right? So let's say like that, and you write O3 in zinc, then you're going to get double bond O on both sides of this, right? So really the same thing twice. I can make it look different like that, but the key is you make ketone. So ozonolysis always breaks